Right, so welcome back to the first official lesson of the spring semester. We are going to be doing some review over a very, very important topic, a very important skill that we are going to need for Unit 4, okay? Oh, well, really for the rest of the semester. And so we learned how to do this in the fall, but I thought it would be really just a good idea for us to review how to do this as sort of a connector between the fall and the spring semester. Okay, so we will start Unit 4 in earnest after this lesson, but for today we're just going to be reviewing ionic compounds. And specifically, the objective here is for you to be able to determine the chemical formula of an ionic compound. Okay, so you might have the name of a formula, and I need you to be able to determine its chemical formula. Okay. You might also have the formula, and I need you to be able to determine its name. Okay, so kind of going back and forth between those two things. So there's a lot of stuff to talk about with this, so I'm going to make it as quick as possible, and then we'll do a relatively short practice assignment over this, and then, like I said, we'll be ready to move into Unit 4 afterwards. Okay? All right, so here's our periodic table. A couple of things that I need you to remember about our periodic table. Number one, the patterns on the periodic table with respect to valence electrons allow us to predict the ionic charges of different elements based on where they are in the table. So remember that all of these elements in the first column are going to have a charge of +1 if they form an ion. These elements would have a charge of +2, +3. We said that we weren't really going to have ionic charges here. Okay, so we didn't, I think we left this blank, or maybe we put an X there, or I don't remember. And then the pattern kind of reverses itself. These elements are going to have a charge of -3, -2, -1, and then once again, the noble gases, these guys don't really form ions. Okay, so you can put an X there, or leave it blank, it doesn't really matter. These 6 columns here are what's important. Okay, the first 3 and then the second set of 3. Remember that we've also skipped the transition metals. Recall that what we're supposed to do in that scenario, let's say we're working with iron, right? So let's say you see a compound that has the name iron 2 oxide. Okay, remember that this Roman numeral is what tells you the ionic charge on the transition metal. So iron would have a +2 charge in this case. Okay, so that's a big way for us to determine the ionic charges is to just use the patterns on the periodic table, which I believe most of you already have labeled on your own periodic tables. Okay, the other big thing that we need to remember from this topic, is polyatomic ions. Okay. So sometimes there are these things called polyatomic ions, poly meaning many. So this is like multiple atoms sort of stuck together in a single ion. And you need to be able to reference this picture. You don't have to memorize these, but you do need to be able to reference this picture in order to use these in different ionic compounds. Okay? And we'll see some examples of this in just a second. All right? So determining formulas. The one big rule, and those of you that paid good attention last semester should remember this, the one big rule about ionic compounds is that all ionic compounds must be electrically neutral, meaning the overall charge must be 0. Okay? The positive charge of the cations, or the positive ions, must counterbalance the negative charge of the anions, or the negative ions. Okay? So let's look at some examples. All right? I think if I jog your memory a little bit, this will... Everybody will remember what they're supposed to do. Okay? So, determine the chemical formula for the following compounds. All right, so we have some names of compounds here. We need to figure out what the formula is. All right, potassium is an element, symbol K. Carbonate, take my word for it. Okay, I'm not going to go back to the previous slide, but on that slide of polyatomic ions, carbonate is CO3 with a -2 charge, okay, or 2 minus, all right? Now, what would the charge on potassium be? Well, that's where you have to look at your periodic table. Potassium is in the first column, so it's going to have a +1 charge, okay? So these are our 2 ingredients, okay? potassium with a positive 1 charge, and carbonate with a negative 2 charge. Then, if we think about what we just saw in the previous slide, the rule about ionic compounds is that the formula has to be electrically neutral. The overall compound has to be electrically neutral. So, what you need to be thinking of is how many of each of these ingredients do I need to make a compound that has an overall charge of 0? Okay? And the answer here is that you would need 2 potassiums for every 1 carbonate, right? 2 positive 1s would counterbalance 1 and negative 2. So your formula here is going to be K2, 2 potassiums, and then 1 carbonate. So K2CO3. That would be your formula for potassium carbonate. Okay? All right, let's look down here at this next one. Iron 3 sulfide. Okay, so iron 3, this is a transition metal, so we need that Roman numeral here. The charge on this is going to be positive 3. And then we have sulfide. Okay, remember that if you see this ending here, IDE, that suffix IDE, that more than likely means that we're just talking about the element sulfur. Okay, so sulfur will change into the name sulfide if it's an ion. Once again, just like we did with potassium, we're going to look at where sulfur is on the periodic table. It's in the column with negative 2 charges. Okay, so 2 minus. All right. So iron has a positive 3 charge, sulfur has a negative 2 charge. How do we make a formula that has an overall charge of 0? It's kind of complicated, right? I'm going to actually draw this one out. So let me give myself 1 iron here. Okay, so there's plus 3, and then here's a sulfur with negative 2. Well, if I just had 1 of each, then my overall charge would be positive 1, right? Positive 3 would sort of, the negative 2 doesn't completely counterbalance the positive 3, right? So I know that I need at least another negative 2, another sulfur or sulfide. But now I have negative 4 compared to positive 3. So now the negatives would be winning. Well, if I keep sort of following this line of logic here, I get to this. Okay? 2 irons, 3 sulfurs. Okay, 2 irons, 3 sulfides. Positive 6 overall, negative 6 overall. This turns out to be the simplest ratio of ions that will make a formula or a compound that has an overall charge of 0. Okay? So the chemical formula then would be Fe2S3. Okay, Fe2S3. That would be iron 3 sulfide. Okay? All right, very good. So that's how you determine the formulas. And then, like I mentioned towards the very beginning, the other part of this is being able to go backwards, right? What if you have the formula, but you need the name, right? So that's the other sort of reversed skill of this that is also important for us to be able to do. This part I think is a little bit easier, okay? The main thing you have to know is that every ionic compound is made of a cation, which comes first, that's the positively charged ion, and an anion. Now there might be multiple of each, right? There could be 2 of these and 3 of these, just like there was in iron 3 sulfide, but it's going to be 1 cation and 1 anion. Okay? You're never going to have 3 separate ingredients in an ionic compound, okay? Or at least not that I can really think of, okay? So what you're trying to do is take a look at this formula here and sort of draw the dividing line. Where's my cation? Where's my anion? Here I have aluminum, and then I've got this, whatever this stuff is, okay? So this looks like my dividing line right here, okay? I've got aluminum, and then whatever this is, and that's going to be your name, okay? Aluminum, that's the name of my cation. This looks like a polyatomic ion, right? I've got ClO2, and then I have 3 of them, right? There's that parenthesis action coming in. So ClO2. Well, if you consult the chart of polyatomic ions, ClO2 is the chlorite ion. Okay? So this is aluminum chlorite, all right? And the reason you need 3 chlorites is because aluminum would have a positive 3 charge. Okay? And so that's why when you use chlorite with aluminum, chlorite has a -1 charge, you would need 3 of them to counterbalance the +3 charge on aluminum. Okay, so that's where that formula comes from, but in terms of just coming up with the name, easy as that, okay? All right, okay, let's look at the second one. NH4,2O. Once again, we have some parentheses here. If you see parentheses in one of these, whatever is inside is going to be a polyatomic ion. That's the only time that parentheses get used in ionic compounds, is when you have polyatomic ions. So my dividing line is going to be here, okay? NH4,2, all of this is my cation, and then this lonely oxygen over here, that's going to be my anion. So this is going to be, it's a polyatomic ion, it's ammonium, one of the only positively charged polyatomic ions, and then oxygen, the name of this is going to be oxide. Remember that if it's just the element, you get that suffix of IDE, okay? So ammonium oxide would be the name of this compound here, all right? Okay, so hopefully this is not completely new to you. I think, you know, the vast majority of you all sort of mastered how to do this in the fall semester. We are going to do a pretty quick practice assignment over this, and then hopefully we're all very good at this and we can move on into Unit 4, where we are going to be using this skill quite a bit, okay? So thanks for watching, and I'll see you guys right after the video.